Welcome, everyone, to the Ontology Summit 2024 Fall Series on ontologies and LLMs. And today we're going to have two speakers, and they will be introduced by our session chair, or actually co-chair of the series, Andrea. Andrea?
Okay. I hope my internet connection holds up because it's telling me I'm a little flaky. So let's hope this works. I am really excited today to have Kurt Cagle and Tony Seale talking. And I just want to introduce them a little bit and then turn it over to them so we can get going. Kurt is the managing editor of the Cagle Report and editor for The Ontologist. He's a writer, he's a speaker, a futurist, a systems architect. He just told us he loved to tinker in all the interesting technical details behind technologies that he uses. He's worked with several Fortune 500 companies, various U.S. and non-U.S. government agencies, and he's been in the business over the last 30 years. He's written 25 books. I've read a couple of them. They're pretty good. And his current focus is on knowledge graphs and AI systems and their underlying ontological dilemmas. On the other hand, Tony Seale has been at the forefront of developing decentralized knowledge graphs, proving their resilience and effectiveness in demanding real-world production scenarios. He's got a whole bunch of experience, too, as a software architect and a programmer. He's built numerous knowledge graphs for different tier 1 investment banks. He's done some interesting YouTubes and writes amazing blog posts on LinkedIn. He's been exploring the synergy between large language models and knowledge graphs. And I think he is also a very influential figure in this landscape. So with those introductions, I don't know, Kurt, Tony, if you want to fight it out, who goes first? I want to turn it over to you.
Yeah, do you want to go first? I certainly don't mind.
Sure, I'll go first. I'll into the breach once more, dear friends. All right, let me press that magic green button. All right, so I'm going to apologize for this. I got when I put together a presentation, I usually start out with a very blank PowerPoint, just enough of an outline to say, okay, this is kind of what I'm going to talk about. And I got to then saying, okay, well, we're talking about AI systems and generative systems. So I'm going to go and play with some of my AI tools. And I spent more time actually putting together the pictures for the damn show than I did actually writing the presentation. So I apologize. It's pretty. It's not necessarily all that terribly useful, but it is pretty. So anyway, the talk I want to give today is on complementary thinking. And that's specifically thinking about the fact that what we are seeing now and what we're developing is essentially a bipolar mode or modality of thinking about knowledge. Knowledge management has been around for a while. I can remember sitting in a conference 20 years ago talking with various people about ontologies and thinking, wow, this is cool stuff. And everyone looks like they're really serious, hardcore philosophical types that are talking about this deep knowledge. And at the same time, it kind of came back to, is this really a domain that is going to amount to anything other than a lot of people sitting around talking about the value of what is a thing? As it turns out, yes, it's certainly evolved in that direction. And it is kind of evolving now so that we are thinking about information, about knowledge, from both the perspective of how do we develop knowledge from a neural net perspective, where we're basically dealing with the way that we more or less, and that's always arguable, but the way that we think about, or the way that our brain thinks about information, that it processes it, versus how do we deal with the abstractions that come inherently with trying to organize information, because the two are not necessarily the same. They are actually somewhat uh, counter in development, in that the way that the way the mechanism works in the background does not necessarily dictate what the best organizational strategy is for the information that we put in. So I'm going to talk about language models, ontologies, network graphs, fair amount of definition. If you're familiar with this space, some of it's probably going to be a little redundant. I'll try to kind of hit the highlights and then spend more of my time towards the end of the talk. Periodically, you will see me looking over here because that's where my clock is. Anyway, thank you for having me, and I'm looking forward to hopefully a good talk. So that's sort of kind of me. You'll notice that the resemblance is not really that terribly great, but this is AI talking about Kurt Cagle. I'm not going to turn it down either. It was kind of an interesting exercise to say, draw me without any reference to me. So there's no camera work involved. It was me basically saying, go off to the internet and have the internet come back and tell me what it thinks about me. Kind of a scary thought. Anyway, I am the managing editor for the Cagle Report and the editor for the Ontologist. These are newsletters that I put out. The Cagle Report is on LinkedIn. The Ontologist is on Substack. Although usually, if the Cagle Report is going to be something that I will talk about what I've produced in the other newsletters that I'm currently writing, as well as on LinkedIn or elsewhere. So it's kind of a summary piece where I get to sit down and talk about stuff that's not necessarily deep philosophical, just stuff. I can be reached at cagle@gmail.com, or I have a Calendly account at calendly.com, semantical. And I encourage people to sign up if you have questions, if you want to sit down and shoot the breeze. It's an opportunity for me to be able to talk with other people in space. So let's focus on ontologies from the standpoint of a knowledge graph. Now, when we talk about ontologies, ontologies is a very, very loaded word. It's the there's a lot of different definitions around. There's a lot of different ways of thinking about ontologies. I find that in general, when I'm talking about an ontology, I'm usually thinking about, here is a way of specifying the underlying rules and constraints and relationships that exist for a given set of vocabularies in a particular domain of concern. There's a lot of overlap with schema. If you actually said, what's the distinction between the two? I'd say there probably isn't a lot. There's some, in the more esoteric areas, because schema generally doesn't deal with abstraction quite to the same extent that ontologies do. But when you talk about ontologies, you're basically talking about how you effectively define the shapes of information, the shapes of knowledge that identify your particular domain. I personally have gotten a little sloppy in that when I talk about an ontology, it does, to me, an ontology could be really anything. A spreadsheet has its own intrinsic ontology. A document has its own, in some cases, several ontologies, depending on how you want to be able to parse it. Ultimately, ontologies are not necessarily something that you tie up and say, oh, it's part of the resource description framework. But if you have the resource description framework, or RDF, it's a very good way of thinking about and organizing the information so that you can communicate it to others. And so, I typically talk about an ontology and in that particular light, in saying that, anything has its own ontology, and we need to recognize the fact that simply because we have a nice shiny ontology that we've defined as some kind of upper ontology or some kind of key ring to rule them all, in reality, ontologies are all over the place and are simply local representations of knowledge or of information that we utilize to be able to communicate thoughts. For purposes of knowledge graphs, ontologies can be identified via URLs or URIs. You can say, this thing that we have has an identifier, and when I have that identifier, then I know that we're referencing this thing. It's a very important concept. It's one of those you don't think about very much if you're used to working with knowledge graphs, but when you start talking about large language models, suddenly you realize that that's not always the case in that particular domain, and you have to really rethink a lot of what you're talking about in terms of identifying the way of identifying the system. So, given that, when we're talking about ontologies, we're talking about sets of assertions. An ontology is generally not the data set, it's the specification, but that specification is basically a specification about how you assert information. The subject of the assertion is the focus of the statement. From a relational standpoint, it's the row ID, although it's not necessarily, a complete one-to-one match. The predicate of the assertion indicates a relationship. The object of the association of the assertion, identifies an object or a value. So it's basically either, some kind of literal, or it's some kind of a foreign key reference. In general, because everything is made up of assertions in the semantic world, it's easy to kind of think, okay, I can take this and move it over to the ontology inherent in an LM. It's not necessarily true, but it's something that we would ideally like to make as true as possible so that we can use one to communicate with the other. Graphs are sets. They're sets of assertions. They are big. They could be billions, trillions. We talk about these billions and trillions of feature sets associated with large language models. Well, realistically, when you're talking about knowledge graphs, you're still talking about millions and billions and trillions, and enough to kind of choke Carl Sagan with his notions of very big numbers. The difference being that when we look at graphs in that regard, we're still largely talking about sets of information that basically form sheets or graphs or molecules or some other similar interconnected network of content. They can be disconnected. There's nothing that says everything has to be addressable or directable, particularly since graphs can be directed. It is possible that you can have a graph where a point can be reached or can be asserted, but can never be reached except by that particular point. They can be disconnected, which means that they can also be distributed. It means that you're dealing with an abstraction here. realistically, we're moving to a mode where the graph is actually larger than its container. Or another way of putting it, the container is essentially essentially overflowing to other containers out there about how we work with these. They can be named, they can be referenced, they can be modeled, they can be selected and aggregated, and put together in various and sundry forms. And in general, there are usually with those structures some kind of schema. It may be shackle, it may be owl, it may be fill in the blank JSON LD. But the idea essentially is that there is a way of describing what is valid for these graphs. Knowledge graphs. Now, what's the difference between a graph and a knowledge graph? None. A knowledge graph is still a graph. It's a very big graph. It's a graph that has multiple ontologies, and in many cases, many multiple ontologies associated with it. And we need to kind of start thinking about moving beyond ontologies from the standpoint of the knowledge graph and the ontology are the same thing. They're not. If you look at how you organize information and you say, I'm going to create a named graph, then that named graph essentially has its own internal ontology to be able to work with. And because it does, we're getting to the point where we have this notion of a knowledge mesh or a data mesh that's been floating around. And I think it was essentially, harnessed by someone who hadn't actually seen what was going on in the semantic space until after they wrote it. But the idea with data meshes is that you have multiple different ontologies that are potentially related, potentially may overlap, potentially may have different ways of describing the same thing. But in general, the knowledge graph is going to be a large aggregate spanning multiple knowledge portals. I talk about knowledge graphs and knowledge portals as sometimes being synonymous. We talk about, hey, look, it's a knowledge graph. And you think about, well, it's a box. No, the box is simply a container. That's the portal. That's how you get to it. The knowledge graph itself is an abstraction. Data shapes. And I should have mentioned shackle in here. I'll apologize in saying, but when you're talking about a data shape, you're talking about some way of identifying the structure of an entity or sets of entities that happen to share certain characteristics. Data shapes are a relatively recent way of thinking about information because they're essentially getting to the point where we're saying, let's move beyond classes. We know what a class is, sort of, kind of, and it's a very arbitrary distinction. Let's talk about a data shape as here's a node. A node has properties. It has constraints. It has ways of being able to work with information. And once you have a data shape in place, you can use it to select and identify. You can use it to validate. You can use it to create interfaces. There's all kinds of things that you can work with these data shapes. They are very intimately tied to ontologies, especially in the sense that they really are moving us beyond schema and into something that is much more fluid. They can actually use, I do a lot of work with data shapes and Sparkle. Data shapes can be used to validate. They can be used for metadata that determines cardinality and constraint and stuff like that. They're also useful for essentially providing documentation and similar metadata that describes for human consumption what it is that you're trying to do with the ontologies themselves. Finally, and it looks like I've got an overlap here. I apologize. I'll have to go back and fix that. Knowledge portals are servers. A knowledge portal or server is a set of related endpoints for knowledge graph servers. So it's a way of basically containing the knowledge graphs that we're talking about. It's optimized for storing, retrieving, manipulating graphs. Any product out there is essentially a portal. And most of those products basically identify, here's a set of endpoints that allow you access to be able to work with information, or work with the information that's contained within these portals themselves. Realistically, again, they're semi-abstract in that they may or may not hide things like sparkle and other things, other similar mechanisms to be able to retrieve content. And we keep moving away, and I think, increasingly I see sparkle as being something that's more and more internal. And I think, to Tony's point, discussing it earlier, I'm sure we'll talk about it more, but to the point where we start thinking about how do you develop essentially context-free ways of being able to query so that you don't have to know what the ontology is in order to be able to get useful information out. This has been kind of the Achilles heel of knowledge graph ontologies for a long time, is that you need to be an expert in the ontology in question. And I think that has stymied or slowed actual development in what can be KGs, from the standpoint of making sure that the information we're dealing with remains consistent.
Hey, Kurt, this is Andrea for a sec. I don't know if you want to jump to the bridging the two, because you've only got like 5 minutes left.
Okay, thank you. I appreciate that. Talking briefly about large language models, and we'll run through this pretty quickly. This is all AI stuff. It's deep learning, it's models, billions of features, extensive corpuses of information. It uses tokenization and prompts. It is considered a form of generative AI, and it has some reasoning capability associated with it. This is the LLM pipeline. It's actually pretty useful in that it basically allows us to think about the fact that not only do we have one way of querying against a large language model, but we also can use these through retrieval augmented generators, or RAGs, to be able to get information from knowledge graphs and incorporate them into the final result sets. These are done primarily through plugins. So you look at what's going on with OpenAI, you have a plugin architecture. Lang chains are processor modules. They're essentially modules that are designed to work with the big pieces. They can be called recursively, and they're typically associated with a single source. RAGs are similar. They're essentially internally designed to work with those keys, typically implemented as plugins. They can additionally add weights to be able to determine what particular nodes of information get passed. And those nodes of information are essentially concepts. Bridging the two. So the key thing when we're talking about ontologies here is a knowledge graph has a number of different characteristics that identify the ontologies involved. They have globally unique identifiers or concepts, schematically defined. They are precise. Once you define something in a knowledge graph, it has a very definite structure. They're explicitly reifiable. You can use mechanisms to be able to refer to particular assertions or sets of assertions within a knowledge graph that's very difficult to do otherwise. They're well-defined in terms of rules and constraints, and it's very easy to switch context. You simply move from one location or one subject concept to another in the overall mix. This isn't true for large language models. Those are contextually defined. There is no global identifier for concepts. There's no distinction between a class and identifier. Reasoning does exist, but it is also basically subject to what was passed into it via the corpus. Relationships are soft and fuzzy, and so they may even vary from object to object when it's in the same class. You have no guarantee that classes are preserved. They have limited reifiability. That's to say that you do have a few interesting concepts where you can basically talk about this or that, or previous or next, but your ability to work with that information is relatively limited. And finally, the context is baked in. You cannot really change that context and once you compile the model. So mapping is pretty straightforward. From an LLM, things like ChatGPT are actually extraordinarily good at mapping LLM concepts to knowledge graph instances. If I basically say, hey, I want this information that I've been working with over here, and I want to turn it into something in schema.org or meme or some other FIBO, I could do so, and it gives you surprisingly a high degree of fidelity if you're willing to go back and double check that, because you have no guarantee that what gets transformed is in fact valid. So it's very good to get to the 80% mark, very difficult to get much beyond that. You can also basically use RAGs to do via link reader in GPT-4 as a way of being able to map data to a schema. And in fact, that's probably a good way of thinking about if you're trying to get the ontologies that you're working with over, this is your entry point into the system. It also helps that I can pass Turtle and other RDF formats into it, and it will understand it. It's surprisingly good at being able to take that. It's a very powerful tool in that regard. Mapping the other way is a little more complex, simply because a good LLM basically is involved in a source question answer format for node assertions. When generating answers, one thing that you can do as part of your training process is to include node URIs properties for your resources and classes. That way you've got a clear way of being able to identify something that happens to come from a knowledge graph and makes it identifiable from references from that knowledge graph. Finally, take advantage of RDFA and similar entity enrichment. Finally, we get to knowledge graph embeddings. They can be converted into vector space representations, which is what is used for LLMs. They are specialized documents that can be added to the corpus that incorporates KG logic directly into the LLM itself. Unlike RAGs, they're part of the LLM. They're not something, they're something that essentially allows that LLM to be able to work effectively and to make reasoning over a limited set. Finally, when they're incorporated, realize that this is something that you're baking it in, which means that you're limited to when you post it, when you bake it, to how great the fidelity is to a knowledge graph itself. A couple of quick questions on understanding what KGs look like. And finally, any questions?
And I think we're going to have to hold questions to the end, Kurt, only because it's time to turn over to Tony. And the other thing we can do is we do have a wrap-up session at the end where I'm going to compile a whole bunch of questions. And by the end of this whole thing, which is November 15th, I want to compile all the questions, all the thoughts, and even the disagreements, because where people disagree is really important. it's a subject of conversation and insight. But I want to first turn it over to Tony, and then if you and Tony have some extra time, we can stay on, but I don't want to cut him out of his time.
Sorry, Tony.
Yeah, no worries, no worries.
And if you could stop
fine.
sharing, Kurt, and Tony, if you could start. Okay, thanks.
Thanks.
Cool. Everyone see that okay?
Yes, we can see fine. Maybe you want to
Okay.
make it a little bit bigger. Well, if I make my screen bigger, it's just kind of, there you go. Thanks.
Cool. Yeah, I have a massive monitor. Okay, so there's some talk that LLMs are just hype or fad. I see that coming up on LinkedIn quite a bit, but less so these days. And I think it's actually a mistake to think that way. They do represent not the end of where we're going to go with AI, but they represent a big step forward. And all of the major companies are heavily investing in them, so it's only going in one direction. They can orchestrate workflows, they can analyze data, they can craft letters, they can generate code, and they can do much, much more. They're going to be enormously disruptive, and all of the companies, from the big ones down to the small ones, everybody's looking at it and thinking about how that we can use large language models in what we do. However, there's a big problem with them. They can hallucinate. And if you're a serious organization, the option to use any of the more generative features of them, the more powers of them, really is restricted down because, you know, for some of us, one hallucination is one hallucination too many. And that's where I think that ontologies and knowledge graphs can come in, because essentially what we can use them to do is place guardrails or constraints around the large language model. So the ontology, as Kurt was explaining, is an older form of knowledge representation, but it has certain advantages to it in that it is. Oh, sorry, getting feedback there. Maybe someone needs to go on mute. It has certain advantages in that it is much stricter, so we can use the two in conjunction with each other, and this I think is a very interesting idea that I've been exploring over the last year or so now, and that is basically that we can use the large language models to help us discover new knowledge, and then we can use the ontologies to compile that knowledge down for future use. And we can think of this as a reinforcing feedback loop. So if you imagine a given question comes in, that question can be referred back to the classes in the ontology or facts in the knowledge graph, which can be injected into the context of the prompt of the large language model, which is then going to influence the way that the large language model is going to reply to the end user, as Kurt again was mentioning. We call this RAG now. And then that response will come back, but perhaps the large language model will also realize, well, perhaps you are missing this concept from your ontology. And then that can go back into a process where now that concept, the large language model, will help you add a new concept into your ontology and extend your ontology. And really, I think this potentially covers the two together can cover each other's weaknesses. Because the weaknesses of ontologies, those of and knowledge graphs, those who've been working with those of us who've been working with them for some time now that know those pretty well, which is that they are quite hard to maintain. They require specialist people to maintain them. They often become stale and out of date. There's a lot of work that goes into basically maintaining a knowledge graph. Large language models, on the other hand, that all comes for free. They have great common sense knowledge and some level of reasoning. They can even do some fact recall, but we can't rely on them. So stick the two together, and I think interesting things start to happen. But within that positive feedback loop, it's also worth saying, here's an opportunity, and this is something close to my own heart, to inject the human into the loop. In some ways, you could see ontologies as a way of humans really kind of getting very strict about how they're conceptualizing the world, and using that as a language to communicate with the large language model. So this is how I view the world. This is how I conceptually view the world, and I'm going to crystallize that down, and then I can save that ontology within whatever Git repository that I'm using. I can go back and refer to it. I can see it. Humans can understand it, but then I can inject it into the large language model, and it will influence how the large language model is working. So I want to drop us down to a slightly lower level here. I won't go too low, I promise, but just to kind of like really drill into this. So when a large language model, what it's doing when it's working, it's basically, we can think of it as a compression of the web. It's basically kind of gone onto the web, it's read every single document on there, and it's looking to do next word prediction. So it's looking at what's going to come next. And when it's doing that, it's referring back using the transformer model to look for relationships between words. I mean, in some ways, we can see that as a graph, and one can make that claim. It would be a very big graph, but we could see that actually as a graph, because essentially the transformer is learning the relational model of how one word relates to another word. And one of the key things that then comes out of that is these embedding vectors, which are, we can see them like a coordinate. So I could give you in two dimensions, I could give you a coordinate on a map, say, and I could say, here's the longitude and here is the latitude. And those two numbers would let you go directly to a position on the map. Now, with the large language models, we're in this really weird multi-dimensional space that represents all of the words and how they relate to each other. So, but they work much the same way. I can take one of these embedding vectors, and it's like a coordinate which will zoom me to the position of king. And I've got another embedding vector, and that will zoom me roughly to the position of queen. And I can do crazy things with this. I can take the embedding vector for king. This is like the canonical example everyone gives of this. I can take away the embedding vector for man and add the embedding vector for women, and that coordinate will now zoom me to the position of queen. So these things are a very powerful way of representing knowledge, but we have to understand that they're existing in this continuous space. That embedding vector, that coordinate, will take me roughly to this area. It's not an exact thing. It's going to take me roughly to that area. It's fuzzy. Okay, and then as Kurt talked about, another way of representing knowledge, and the older way, the one that was the most flexible, the best way that we had until large language models came along, is representing them in a discrete format of graphs. So we can say we've got a king and he's a man, we've got a queen, they're a woman, they're both part of the royalty. Now, knowledge graphs in particular, and again, Kurt alluded to this, are really discrete. You know, they are as discrete as you could possibly get, because what we actually do is we give a URI, which we might as well call a URL if we're making it resolvable over the web, to each and every item within the graph. So then I can zoom into the node. I could be anywhere in the world, and I could open a web browser, and as I put that discrete location into the web browser, the DNS system is going to resolve that for me, and it's going to take me down to an individual server, and it's going to locate me there. And that is as discrete as you get. We put a boundary around that concept, and now I can globally identify it from anywhere in the world. So we can think of this then as two fundamentally different ways of representing knowledge. This is a mathematical concept of continuous representation, which is brought to us by the large language model, and a discrete representation, which is brought to us by the knowledge graph. They're both ways of representing knowledge, but they're kind of fundamentally different in a way that kind of pierces down deep into mathematics and really to, I guess, to a certain extent, to the fundamental nature of reality itself. So, yeah, and what I think is interesting here is to think about the way that the human brain works, because there is an idea that I'm quite fond of about there being a system 1 and a system 2 in the brain. So our system 1 is effectively this intuitive system. Any task that we really nailed down and learned, or anything that we do kind of instinctively, that is existing, and that's in this kind of really fast, intuitive space. And the analogy we can make here is that's like the large language model part. It's this continuous space. It kind of zoom. You can zoom around. You can blend concepts together. You can do all the LLM magic. And then we have system 2, which is when we're doing a bit of logical reasoning or some hard mathematics, or we are wiring in a new skill, building a new conception of the world. And that represents here for me the knowledge graph. And it's not like one is right and one is wrong. Actually, what's super exciting is what happens when we bring the two together. So how do we bring the two together then becomes the next question. There's a lot of ways to do this. The typical way of bringing them together is the RAG way. So it's basically, I'm going to use the large language model to generate me a Sparkle query or some kind of graph query, and I'm going to go off and execute that as against the knowledge graph. And then I'm going to take the results of that. I'm going to inject it into the context of the LLM, and I'm going to ask the LLM to do something bearing in mind the context that I have pulled from the knowledge graph. That's one way, but there's a lot of ways. And I kind of want to zoom out a little bit from that and just kind of, well, I'm going to look at 2 different ways. But the thing to focus on, I think, is this notion of continuous and discrete representations. And what is it that we can do to narrow the gap between the two so that we can, as far as possible, harmonize them? So here's one example of how one can do it. So in pretty much every knowledge graph, you're going to have a description of each node. We tend to use this like RDFS label for the short description, and then quite often DC description for the longer description. So in this example here, in Python, for those that do it, you're just doing a select query and we're pulling out every single description. Then in the next thing, what I'm going to do is I'm going to take that description and I'm going to call out to OpenAI, and I'm going to get an embedding vector for each of those descriptions. So here we've got a description of Jennifer Anderson, and I could pass that text into my large language model. And now I will be able to store this discrete node relates to this textual description in embedding vector space. And then when a user came in and did a query, I could turn that into an embedding vector. And then I could go to my store and I could find those embedding vectors which were closest in this continuous space to the question that I've now asked, and then I can find the related node within the discrete graph. It's one example. Let's look at it another way. Like, interestingly, what people do with the embedding vectors is they stick them into vector stores. So basically, you churn through your document, you chunk it up into like sentences or paragraphs, however you want to chunk it. You create an embedding vector for each one of those, and then you store it down into one of these vector stores. Now, that obviously is in our continuous space, but here you go. Here's a really interesting thing, and personally, I think this goes pretty deep. What's the algorithm that is emerging as the most efficient way to then query these vector stores? It's a graph algorithm. It's this hierarchical, navigable small worlds algorithm. So how does that go from, how does it go kind of the other way? And I apologize for anybody if this is kind of a bit technical, but basically we can think of that continuous embedding vector space, and then we can think of like nearest neighbors to a given, so a given embedding vector, queen, it's going to be quite near woman, it's going to be quite near royal, they're kind of neighbors. And we can set a discrete boundary. So we're going to say we're going to go out within that nearest neighbor, within the embedding vector, we're going to go out like 3 hops, say. And that's kind of my boundary. And on the bottom of the algorithm, here is all of those. And we stack that all together, and now we basically got a graph representing the embedding vector. So that's kind of the step where we've gone discrete. And then what we can do with this hierarchical version is that then we can basically look at how many inward pointing edges that a given vector has, and the most popular ones, the kind of hub ones, we'll elevate them up to the next layer, and then we'll elevate up to the layer above that. And this is basically the algorithm that then is built into, Elasticsearch is adding vector search into it. MongoDB is adding vector search into it. They're all using this hierarchical, navigable small worlds. So that's interesting, right? There's something fundamentally, I think, going on there, that we can basically say that language, what the language is almost like a process where we take a continuous space of conceptualization of the world, and then we take a word and we capture it and we put a boundary around it and we put it in the dictionary and we write it down and we say, here are the synonyms that relate to it. And then the large language model has taken all of the words that are on the internet and it's scanned over them, and it's using its attention heads to look for the relationships between those words. It's kind of like decoding that, and it's putting it into this continuous space to create the embedding vectors. And then when we come to search it back on the other side, we're reversing the process out and we're putting it back into a graph and into discrete space. So all of this stuff just makes me think there's something fundamental going on here between these two. And then it comes to the question of, well, what if all of your data was actually in a graph? So we're basically saying that the text data, as you're kind of reading it through and chunking it up into these vectors, and then we can use a graph-based algorithm in order to understand it. What about if my data was in a graph as well? And so the pattern that I'm proposing around here is, I'm calling like the working memory graph. So if you imagine that I have whatever my underlying data is that's in my knowledge graph, I've now got that in a kind of graph format. So I can go, a question can come in natural language. I can go to my knowledge graph and pull out a chunk of graph-shaped information that's related to that, either generating a graph query or using the technique that I showed before. So that's going to give me a bit of context. I can refer back to the ontology using something similar, and I can go and grab the concepts there. I can put that as the context within my large language model and pass that into the large language model, which is then going to come back in a response. But one of the cool things about the large language models is I can say, give me the response as a graph. Use these well-known URIs to identify companies or people that you find, for instance. Use Wikidata to be the URIs that you identify, so that now within my organization I could have a simple mapping table to map back to concepts in my own graph. I get the results, I bring them back. I can now apply my ontology to the graph that I've got there. Does this make sense? Is it I can use reasoning across this graph, like in trustworthy reasoning. Does the response fit my ontological worldview? Is it reasonable? Does it make sense? Is there potentially outlying hallucinations in here? Do the facts that it's pulling back match the facts that I'm recording in my knowledge graph? I think are important. And it can do a whole bunch of other things that I won't necessarily go through, but it can use the graph to actually reason through the process. There's a lot being made of LangChain is chain of thought, which is very powerful. But then there's been subsequent algorithms saying we can squeeze a bit more out of tree of thought. So okay, we've got a list, a chain, we've got a tree, but next level up from that, that's a DAG, a directed acyclic graph, and that's basically kind of what we use in pretty much all ETL processes now. So perhaps even the way that these things get chained together may end up in a graph format. And as we talked about before, if there's ontological concepts that are missing, we can have a pipeline where the ontology gets built out. I'm gonna rush the last bit here because I think I'm running out of time. But let me just kind of sell you in a vision here. So, how does this matter to businesses? Well, with your kind of schema over the top of it, with your ontology over the top, you can basically put adapters, as Kurt was talking about. Like if you think about a data mesh, now imagine in that data mesh, each data product was publishing up a kind of graph fragment, and that graph fragment related back to ontological concepts which were stored. So now I've got a semantic layer through which I can use business concepts to access data which is in a graph format, then if each of those graph adapters basically had one of these working memory graphs in it, it's got like a large language model combined with this graphy format, and that is all operating through the semantic layer, I could do things like go and do a search over all of the information that's existing within my company. It's going to go out to the semantic layer. It's going to route it to the correct data product that is the expert in that field. And I think for me, this is important, because the LLMs do represent something very big, and to not see that and not see the direction of travel, I think is a mistake. To dismiss everything as, oh, it's just this fad, or it's not. This is real. The world is changing, and we all need to pause, I believe, and think about what we want this world to look like as these massive changes come in. And one of the things that I think is potentially a better future, or lays the foundations for a better future, is to have a network of networks. So as opposed to basically all of the data and all of the large language model and all of the AI collapsing into like a few of these massive gravity wells, like this gives, if every organization begins to adopt this pattern and adopt it early on, then they can basically connect all of their own information together into a sort of semantic data mesh. And then we end up with an AI future where we've got a network of networks. And that's a powerful pattern. And I believe the fact that ontologies allow us a way of communicating, if you like, at a conceptual, abstract level with the large language models, then maybe also lets us put our own guardrails, our own expression of our worldview into the large language models, which is, I guess, why I'm passionate about this and here to share my views on it. Thank you. Thanks for listening.
Oh, Tony, that was amazing. That was really interesting. Kurt, yours was too, is a really nice setup. Maybe we have, let's see, about 8 minutes before the time's up. Does anybody want to raise their hand, ask some questions?
I always do.
Ravi, I can always count on you.
Yes, I have two questions, one question for both of you, Kurt and Tony. You have largely concentrated on feature space or clustering algorithms. You have any comments on learning sets and machine learning in that context? Number one. Number two, I like the analogy of analog and digital domain. I'm a quantum physicist and I've been always thinking analog. So your two parts of brain is excellent. Can you tell us which is more real?
I think I think the danger here is basically getting into what's real. What do we mean by what is real? When you're looking at when you're looking at what Tony has laid out, and I think it truly is a very good view of this particular domain. What we're looking at realistically is just different patterns of organization, different ways of being able to say, how do I represent knowledge? How do I represent information? And it's not really any different from what we've been doing for the last 30, 40 years, except for the fact that the tools we have now are order of magnitude more powerful, order of magnitude faster. And so we're getting to the stage, and I've been talking about this for years. I mean, we're getting into the stage where we're dealing with basically the fractal nature of information. And it's kind of weird because it's you can't specifically point to anything and say in and of itself, hey, this is a fractal. but you really do get a sense as you start working with all of this that the fractals are there, that you can see self-similarity basically building its way through different levels of abstraction for each of these. And I think that's one of the consequences. I mean, if you want to talk about, a quantum set basically is fundamentally quantum mechanics deals with the consequences of both discrete boundaries or energy levels that have to be maintained, and the corresponding characteristics of like the Heisenberg relationships, where if you do know one, you can't know the other to the same degree. There's always going to be trade-offs in information, and that's key. Tony?
Thank you.
And yeah, I wanted to turn it over to Tony, and then I want to give time for Jason to ask his question too.
Yeah, I would just say that one isn't necessarily better than the other. I think they have different advantages, and I think it's basically this kind of flipping between the two. Like we go from discrete to continuous to discrete to continuous, and there is advantage in both representations. I mean, which one? If you speak to different people will say different things. You ask Stephen Wolfram, and Stephen Wolfram says, "Yeah, the world is discrete. It's like a massive hypergraph what he calls the Rouliad." Other people would come and say, no, the world is, you go to speak to some Zen Buddhist and it's all continuous. It's probably the sort of thing we're never going to get an answer to, but being able to shift in and out of representations is, I think, crucial for knowledge, which is why bringing these two together, I think, is so important. Like the graph representation is the best structure that we have. I mean, probably a hypergraph, but the mathematics is a bit more complicated than what we would engage with right at the moment in a business context. But the graph is the best structure that we've got for a discrete knowledge representation, and the LLMs are the best that we've got on continuous. So stick them together, and from my experiment, magic starts to seem happening.
Thank you.
And Jason, if you want to unmute and ask your question.
Sure. Hi, my question is to Tony. With regards to this semantic routing and semantic data mesh, I was wondering if that's being used for the integration of data stores between UBS and Credit Suisse, and whether that's including trade stores for reasoning about trading strategies, or whether it's including knowing your customer for sanction screening, use cases like that.
Yeah, I mean, I'm afraid I'm here in a private capacity speaking for myself, so anything to do with UBS, I'm afraid I can't comment on.
Okay, no worries. Thank you.
Sorry about
that. Anybody else? And we do have 2 minutes. Maybe I will just kind of say, Kurt, could you make a comment on?
Jason has his hand up.
Oh, Jason still has his hand up.
Still has his hand up.
Lowered now.
Oh.
Yeah, Lord.
I have a brief comment. You've been talking about knowledge graphs and occasionally mentioning reification. So I thought about that problem from a more technical kind of point of view, and came up with a way of dealing with representing knowledge graphs where every edge is reified. So that you can refer to it like anything else. Edges become first class. And I developed a nice simple language, extension of Sparkle, where one can query these graphs quite effectively. I developed the denotational semantics for them, so you basically tells you how to implement the language, and it can be stored right now on a triple store. So this was part of an earlier summit that dealt with knowledge graphs. So be interested to hear what Kurt and Tony think of that.
To me, reification is actually a fairly fundamental problem or fundamental characteristic of information, because we are, with reification comes discoverability, and this is actually going to be one of the big issues that I see with LLMs. I remember seeing one paper that basically talked about how do you effectively identify where in an LLM a particular concept is. And the answer kind of came down to, well, okay, you put a probe into the LLM and see what shows up. And I thought, okay, we've now reached a point where we are developing electroshock therapy for our information spaces. But realistically, I think that once you start talking about reification, you're talking not only about, with reification comes things like probabilistic interpretations, Bayesians, functional specifications, where you can essentially say, okay, I have a graph, and a graph has a point to a concept that happens to be a function, and that function in turn has these characteristics and is continuous. And I think that's actually kind of where we're going with a lot of this. So, I have been working very closely with reification as part of the underlying, getting out the word about how this technology is important. I'm just now also getting to that same stage with LLMs, because in many ways, I think that domain is actually going to be much harder to be able to say, how can we find information about the information that we have? And how can we judge verity? How can we judge consistency and other characteristics that are not specifically factual from the standpoint of the knowledge contained in the set itself?
We have two people with their hands up.
Yes, thank you for your talk. It was fantastic. I have a question. Have you thought about leveraging a graph algorithm to with LLMs to simulate some kind of reasoning? For example, we can use a entity detection algorithm or any kind of graph algorithm, because what you just explained is that you only query simply the knowledge graph, but I think that we could use, for example, graph algorithm for use knowledge graph to simulate reasoning with an LLM. I don't know if I am clear, so thank you.
Yeah, no, absolutely, and this is really important with reasoning paths as well, I think, and actually, one of the things which I'm playing around with at the moment is whether you can just use the LLM to do all of the compute side stuff. So there's a very interesting recent paper that came out where they basically used the LLM to do node classification. So one would imagine that a graph neural network would always beat a generic LLM at doing a graph specific task like that. But actually, this paper showed that the LLM outperformed the state of the art with graph neural network for this node classification task. So one of the possibilities is that at least in this kind of short term, that we use the LLM for the compute side in order to simplify the structure. But then you're basically kind of what you do is you you pull into the graph, you pull back node paths, you pull back information from the graph, you transform it into natural language, and then you pass that into the LLM to do the compute on, and then and that's, I think, probably going to take us quite far, is my initial feeling. And then only dropping down to like specific like GNN algorithms, you know, once you need them. But certainly reasoning paths, are going to be fundamentally important, and as are a whole bunch of other kind of like finding shortest paths in the graph and clustering and stuff like that. It's just whether actually some of the compute, maybe it's more like I just do a query into the graph, I pull back the information, and I hand over to the LLM to actually do some of the compute.
Thank you.
One other point on that to consider. This stuff is literally changing week by week. And so, you know, a lot of what's going on now is really trying to figure out where in the architecture this is going to happen. It's not that people aren't aware of, hey, you know, you can do this. I mean, that's what a graph embedding does. You know, what paths do. It kind of becomes a question of where in the particular architecture that we're dealing with is the best place for this kind of information to exist, for which purposes. And I think that's really where we're going to see a lot of the development over the course of the next year, is not so much the fundamentals as it is increasingly the engineering.
Yeah, I'd really agree with that. There's going to be so much volatility. But one message which I'm trying to get out is, if this hypothesis about the discrete and continuous is true, then there's one thing, which is getting your data into, as much of your data into a graph, and much of it is mapped into the ontology, taking the data-centric approach as you possibly can. That is still going to take quite a lot of time, and all organizations should be embarking upon that as soon as possible, in my opinion. If this theory is correct, that bit's going to take time. If your competitors are doing it, you want to be getting on. We're doing it right now. There's no, you know, even with the LLMs involved, there's no magicking away the hard effort that's got to go in, the graph people have got to put in to do this.
Yeah, I have a question. So I think partially it was just answered by Kurt and Tony. You know, so it's been quite disruptive. You know, LLM in this space. You know what knowledge graphs were trying to do with bringing in knowledge into all the aspects. You know, what's the kind of down the road vision that we see? Do we see LLMs completely, you know, eating up all the knowledge graphs and, you know, off the shelves LLMs available with no efforts to be put into creating the ontologies and enterprise level knowledge graphs? Do we see that happening, you know, sometime soon or down the road?
It's possible. I mean, basically, if LLMs sort out a couple of things, so if they sort out the hallucination factor, and they sort out being able to write back to themselves, then yeah, arguably everything collapses into that one architecture. I don't see that happening in the near term. So if you're a business or an organization that's looking for a strategy to kind of get you through the disruptive change that is coming, my strong recommendation is get as much of your data into a graph as you possibly can, and get as much of it mapped into ontological concepts as you can, because in this medium term, that's your safest strategy. What happens in the future beyond, it's going to get very hard to make calls going out beyond 10 years, because it's really going to go quite crazy in a way I think that most people are underestimating at the moment.
Years. I'm saying 10 months. On that point, you know, I think the other side that I see happening right now is that we're decomposing LLMs, you know, right and left. You know, I actually prefer the term community language model, because I think it gets a little bit closer to where we're going, which is essentially decentralized, federated, capable of creating ad hoc networks of information from a wide variety of sources. I mean, what we're seeing right now is essentially the revenge of the integration. You know, the ability to be able to create ad hoc knowledge networks is really going to be the immediate consequence, and it's not going to be one size fits all ChatGPT everywhere. Because it from a business standpoint, no one is going to want to have that level of monopolistic control for any competitor.
That brings me to ask a quick question. Where do you see the trust and security kind of certification in AI effort?
Oh God.
Yeah, I mean that's a big danger for them. Large language models are susceptible to adversarial attacks. So again, this is another reason to get your data into this linked data mesh, because what you can do is track lineage down. So if you're thinking about training these things, you need to know the lineage of the data that is going into the training of them. So if there's some information which is private to your organization, you basically need to think of it like a cell wall. Like your organization has now got a cell wall around it, and what I want to do is I want to network all of my data within that, and I want to have like an ontology to describe it, and I want to have clear semantics around what can be used in what scenarios, so that then when it comes to any LLMs which are exposed at the entry point for that, you know what's going into them, and you know that very clearly. Because if you don't, your competitors are just going to kind of see through you. So as they adopt this pattern, as they kind of LLM up and connect all of their data, the signals that you're leaking out of yourself will just mean that, your competitors will just be able to see exactly what all of your strategies are and what you're doing, because you're just basically leaking all of your information out into the web. So yeah, it's definitely an important component.
Thank you.
You're seeing the move from prokaryotes to eukaryotes, actually. I think there's I love Tony's illustration, the last one there. I saw it first a few weeks ago, and the first thing that I saw when I thought when I saw this was, that's a cell diagram. It's a biological looking thing. We're reaching the stage where computing and biology are essentially now becoming one. A little frightening when you think about it, but it's really, really cool. There's no question about that.
Would the speakers kindly read the chat questions, which we will post on the wiki page, meeting page?
Ravi, we will do that. I do want to say we are now 15 minutes over, and we've taken a lot of Tony's and Kurt's time. So we can continue the discussion, Tony, Kurt. We do have an Ontolog 4 mail list.
I do have to drop, I'm afraid, but
Yeah.
I've really enjoyed being here. So thank you for inviting me. It's been a real pleasure.
I love the conversation. I hope you'll come back and we can do some more.
Cool. Thank you.
Thank you. Bye, everybody.
Well,
Bye-bye. Thank you
Bye.
very much.
Thank you so much. Mike Bennett has been there, but have been silent little.